All right. I will begin with a word of prayer. Sorry again for the delay. Dear Father, we thank you for this day. Again, I thank you for this class and these students, and thank you for the break that's about to start. Help us to glorify you what we do and just understand about eigenvectors and diagonalization today, Lord. In your name I pray, Lord Jesus. Amen. All right, so you guys, I gave you a problem to chew on before class. It was the matrix. You put it up here. And you guys, at least one of you told me you got eigenvalues 4 and 2. Very good. So the matrix was, and if I'm copying this matrix down wrong, please tell me. -2, 0, -4. Oh, wait a minute. Sorry, I'm on the wrong page. That's for the this is for calculating the eigenvector. What I wanted was 0, 0, -4, 2, 4, 2, and 2, 0, 6. And what I wanted to do, as opposed to just calculate that, because this is, by the way, example 6.2.13, right? 6.2.13. It is that example. So, of course, you can look in the notes there to see exactly how to calculate the characteristic equation. And the characteristic equation is a little bit fussy here, right? If you guys really worked it out, it should have taken you a few minutes. That was my my idea, right? So I'll just say what happens is if we look at the determinant of a minus lambda I, I'll skip the steps here, but it works out to minus lambda minus 4 squared times lambda minus 2. So we get eigenvalues, let's say lambda 1 equals to 2 and lambda 2 equals to 4. This guy has algebraic multiplicity of 2. This one, of course, has an algebraic multiplicity of 1. And as we work through it, you'll find that the 2 eigenspace, which is the null space of A minus 2I, it actually can be written as the span of -2, 1, 1. So that's my eigenvector with eigenvalue 2. And on the other hand, my 4 eigenspace, namely the null space of A minus 4I, short calculation shows you that, in fact, that you have 2 dimensions. So the span, you can use 0, 1, 0 and -1, 0, 1. So, you know, the choice of basis, that was supposed to be a squiggle bracket. The choice of basis is never unique, right? You can always, like, multiply by a number or divide by a number, a given vector, and it doesn't really change what the span is. But that's that. Now, what I wanted to show you guys was a way to check your answers, and you guys are probably like, we've got ChatGPT. We don't need your silly websites. But I don't know. Does ChatGPT do eigenvector problems? No? Yeah, I don't know. I think my son has said that if you try to do certain technical mathematical things with ChatGPT, sometimes it's just like box. It's like, too hard, technical mathematics or something like that. But there's more than one AI engine out there, right?
I haven't tested this kind of problems, but ChatGPT can make mistakes with matrices.
Right, yeah. I think, so, yeah, I mean, in the same way, like, you know, when I work on my art, and I am working on generating, you know, prompting my art. I find that if I want to make something simple, like, I don't know, I want to make the word cat burglar on the wall or something, it'll like put it in a Russian font or something stupid, right? Like, it just doesn't do well, the AI picture generator doesn't do well with just basic things that if a human illustrator was doing, it would just be it'd be the easiest part of it, right? So the current generation of AI is not very good at certain aspects of clearly defined tasks. On the other hand, I think like Dr. Schweitzer is using it to help him write a book. So, I mean, or design a course. Like he's, it like suggested a textbook and he's like bouncing ideas off of it. He told me he was like 150,000 words into a conversation with it. So, given that there's not another faculty here who has his particular set of interests, it's super useful to have somebody to talk to, even if you're talking to yourself. But you're not talking to yourself. You're talking to yourself, talking to the combined intelligence of the internet, which has been stolen through a massive information grab through an unethical AI. Well, at least that's that one guy said, but he's dead now, so we can't really know.
JFK?
No, not JFK. This is much more recent. One of the four inventors of ChatGPT he suicided himself. Tucker Carlson did an interview with his mom. It was like an hour long. I'm told we can't trust it, though, because it's Tucker Carlson. So let's see here. Somebody's like, well, why would they go to Tucker Carlson? I'm like, because no one else would talk to him, maybe. Her, actually, his mom, who's like, my son didn't commit suicide. No one commits suicide after going for a month-long vacation with your friends in the tropics. You just come back to kill yourself without opening your packages. It's weird. Anyway, it goes on. If you guys can find it. It's like an hour-long interview. Okay, I'm digressing. This is why I need to eat breakfast before I teach class. So on my website here, the website for the course, number 5, this will beat the current generation of AI, I'm pretty sure. This is a German website. Not that that's terribly relevant, but arndtbrunner.de. And I usually click on the old version of the calculator if I'm being fussy. And the format here is stupidly easy. Well, first of all, look at the basic one that's in there. So I wanted to talk to you guys about this because, yes, we could use MATLAB, and we probably should learn how to use MATLAB to calculate eigenvectors and stuff. And I will eventually get back to that. Like, we will talk about MATLAB in here in time. Just not today, except that I'm telling you I'm not talking about it, which begs the question, is that actually talking about it? These are the kinds of questions I ask more of if I haven't had breakfast, so let us go on. Not good questions, just questions. Let me make it bigger. There we go. So here the default matrix that's put in there, 7 minus 2, 5, 9. It gives you this characteristic polynomial. Hooray! So, by the way, this website does the determinant. Their characteristic polynomial is determinant of lambda I minus a, all right? Or maybe we could put an x here and say that this is p of x, all right? This is the, doing this will make this equal to x to the n, and then stuff. And then the last thing, I believe, would be like minus 1 to the n. Well, anyway, plus stuff. Let me not speculate here. But the point is that if you set up your characteristic equation like that, it makes it what's called monic. It makes the polynomial monic. The leading coefficient's 1. For us, I have been teaching you guys to look at that's minus my p of x. See, our p of x is the determinant of xi minus a, let's say, right? And so what that ends up meaning is that like p of x is x minus lambda 1 and so forth, If there's n eigenvalues, and there's a minus out front. Well, there's not a minus out front. There's actually, this all multiplied by, it all gets multiplied by minus 1 to the n, right? And you've seen this in the examples we've worked. For the 3 by 3 examples, the characteristic equation had a leading coefficient of -1, right? The 2 by 2 examples, if you look at them, it had a leading coefficient of 1. If you look at 4 by 4 examples, we'd have a leading coefficient of 1. 5 by 5 examples, if I had any, the leading coefficient would be -1. Why do I do what I do? And here, why don't I use x? Why don't I do like the variable times the identity matrix minus a, the determinant of that, or for us, lambda? Here's the reason. I've tried both. In the past, trying the other, it goes worse for students. And the reason is simple. If you do xi minus a, that means you have to put a negative sign on every component of the matrix. There is like n squared opportunities for a sign mistake there. And you guys will make those mistakes. So as a point of making the arithmetic go better, I always do this as opposed to that. Because there I just put minuses on the, we just put my... Seriously? Good gracious. Really? All right. No. Goodness. I tell you what. Maybe I should just kept sleeping. Those are different. All right. And I actually don't, I should put a, rather than calling this Q, let me call it Q, all right. The relation between these is that Q of x times -1 to the n is equal to P of x. Like that's the relation between these two guys. They're either equal in the case of even dimension, or they're off by a sign in the case of odd dimension. Really? Come on, come back to us.
Should that be negative Q of x? Or is it?
No, I'm saying P and Q are different. Like, all right, let me stop talking about this. This is accomplishing nothing. I'm just telling you why I do lambda I minus a versus a minus lambda I, just to keep you guys out of trouble. But whichever we do, there's lots of opportunities for mistakes here, of course, because it's a numerically challenging problem. Like this one would be a nasty test question because the eigenvalues are minus 8.34 and 6.34. Well, apparently all these digits as well if you wanted them, right? So that means that like the characteristic equation does not factor nicely, right? But this website's pretty cool in that it gives you the eigenvectors right here, right? And then you can do other things like currently the norming mode, which norming means length. So the length of the vectors are set to be 1. We can make the first coordinate 1. It would be another choice. And then that's what the eigenvectors would look like if I make the first coordinate 1. So it'll do that for you, that kind of thing. All right, so the one we were just looking at was 0. But I love the syntax here. It's very simple. 0, 0, minus 4. And then 2, 4. You just put spaces between the numbers and hit return for the next line. Like the syntax here is very, very, very nice in terms of like if you're, doing it. And then, all right, come on. So the characteristic polynomial is actually x cubed minus 10x squared plus 32x minus 32. Of course, we'd have a minus on ours because of what I was just talking about. As you can see, the real eigenvalues are 2, 4, and 4. Hooray. Uh-oh. Eigenvector of eigenvalue 2, 1 minus 5 minus 5. Does that comport with what's in the notes? See here, if we took this and we did what? Divide by minus 2, what do we get? If you take the one I wrote and you divide this vector here by minus 2, we get 1 minus a half minus a half. That's that. If you take my, look here, you got 0, 1, 0 and 1, 0 minus 1. Again, it's almost the same. What's the difference? Yeah, this one we get 1, 0, minus 1. So we've multiplied the second vector by minus 1. But, so this is the kind of ambiguity we always face with finding eigenvectors, all right? Any questions? But you guys can use this to check your homework. When the focus of the problem is not just finding the eigenvalues and eigenvectors, like you're just using it as part of a larger task, especially if it's like a take-home test or or homework, as we often call them. You're, of course, free to use this website to like calculate eigenvalues and eigenvectors, all right? Or you could use MATLAB if you want to figure that out. I'll eventually help you with it. Or if you're, if you're sufficiently educated, you could try to use ChatGPT, but you have to use that with both eyes open because it does say crazy stuff like, because since 4 is clearly less than 2, blah, 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 blah. Like it says stuff like that, right? That's what Dr. Schweitzer was saying. Is like, I don't think he's using ChatGPT. I think he's using Grok or whatever, but all right. Excuse me. So we need to talk about diagonalization. What does it mean to diagonalize a matrix? And can we diagonalize this matrix we're looking at right now? What do you think? Well, let's talk about it. Let me define it and work it out for you guys. All right. So to diagonalize, can't talk. Diagonalization of a matrix. So given square matrix A, let's say, in well, I'll talk about our n by n, but we could just as well talk about a complex n by n matrix. But given a square matrix A and n by n, if there exists an invertible matrix P such that P inverse AP is equal to a diagonal matrix D, which is like, let's say, diag of D1, D2, Dn. So that notation is just a sneaky, quick notation for this matrix, right? Like, can you guys think of another way to express a diagonal matrix? Like, what is this? Another way of looking at it would be what? This is what? I'll start you out. It's D1, E1, concatenated with what? The first column is D1, E1. The second column in a diagonal matrix is what? Can I get a D2, E2? D2, E2. How about a D2, E2? Yeah. Sorry to those of you who started your break early. My camera work is as substandard as everything else today. So we got a D2, E2. All right. And this goes on until the last nth column is Dn, En, right? So that's what we mean by a diagonal matrix. Only non-zero entries are on the diagonal. So my question to you is, what does this have to do with eigenvalues and eigenvectors? Like, why am I even talking about this? Well, check this out. If we do, if we multiply this equation, all right, so let's see here. So here's the theorem, and I'll try to work it out for you guys. But the theorem is this, which is that A is diagonalizable if and only if there exists an eigenbasis for A. Yeah. Moreover, if that eigenbasis beta is V1, V2, Vn with eigenvalues lambda 1 through lambda n respectively, then the basis matrix inverse times A times the basis matrix again is in fact equal to a diagonal matrix where the diagonals are the eigenvalues. So yeah, not only does the eigenvectors and eigenvalues have everything to do with it, they're everything to do with it. Let me see if I can work this out. Famous last words, you know. Let's see here. So, suppose that A VI is equal to lambda I VI for I equals to 1, 2, da da n, and assume that your set of eigenvectors is linearly independent, right? If that's the case, we're talking about an n by n matrix that gives us what's called an eigenbasis. What's an eigenbasis? That's just a fancy word for a basis of eigenvectors. What's a basis? A basis is a linearly independent spanning set, right? So for us here, that means n linearly independent vectors. So, if we let beta, right, equal to the basis matrix here, right, then if we let basis inverse be, let's see here, if we let its columns be like W1 through Wn, right? Not columns, I said columns, I meant rows. Has what? If we do like beta inverse times beta, how's that work out? So we do what? We do like row I of the inverse matrix dotted with column J of the basis matrix. This is equal to, specifically it's equal to like the Wi vector dot with the V vector, and that's given to be Kronecker delta Ij because we're assuming that we've got an inverse matrix, right? I'm writing this out because I'm pretty sure I need it for the calculation that follows, okay guys? So let's calculate then beta inverse A times beta, all right? So we'll keep the beta inverse over here for a second. And A times beta is really what? That's really A times V1, A times V2, A times Vn, right? Do you guys follow me so far? I'm just using the column by column multiplication rule. But these are eigenvectors, right? So what are those? We've got lambda 1 V1, right? Lambda 2 V2, lambda n Vn. All right? And then how do I do that calculation? Well, remember that this beta inverse is really a stack of W's, right? So if you look at this, the ijth component of it looks like what? You've got just what? You got W, basically Wi dotted with lambda j Vj. That's like the arbitrary ijth component of this matrix, right? But lambda is a constant, so it factors out of that. And what's the dot product of Wi with Vj? It's Kronecker delta Ij, right? So in other words, beta inverse A beta the ijth component of it, right, is equal to lambda j Kronecker delta ij, which is just another way of expressing the fact that beta inverse A beta is in fact equal to lambda 1 E1, lambda 2 E2, lambda n En, you see. Because it's only non-zero where I is equal to j, right? And that non-zero entry is lambda. So this calculation proves that if we have an eigenbasis, we can diagonalize the matrix by doing the basis inverse matrix times the basis inverse matrix. Basis matrix again. This is a very specific thing. We've talked about it a little bit before. I should talk about it more some other day, but this is an example of what's called a similarity transformation. Similarity transformation is when we take a matrix and we pre and post multiply by a given invertible matrix and its inverse. And it turns out that if you have an eigenbasis, we can do a similarity transformation to diagonalize the matrix. All right? The converse direction, if we have that P inverse AP is equal to, the diagonal matrix D1, Dn, what happens if I multiply that equation by both sides by P? What do I get? I get A times P, right? I get A times P is equal to P times this diagonal matrix, right? So what does that mean? Well, let's give a name. Let's let P equal to V1, V2, Vn. And here, like this part of the I'm not assuming that these are eigenvectors at the moment. I want to show you that they are. It follows from the condition P inverse AP equals to a diagonal matrix, right? So if I let P be this, oh man, AP is equal to, well, AV1, AV2, AVN, and on the other hand, that's equal to DE1, DEN. What's this mean? Oh, my bad. I was supposed to do, I have to multiply the P through over there too, right? I've got what? I've got D1, PE1, DN, PEN. What is PE1 though? What happens when we take a matrix and multiply by E1? It picks off column 1, right? So column 1 is V1 in my language here. So you got D1, V1, likewise D2, V2, all the way out to DN, VN. Aha! So thus AVJ is equal to DJ, VJ, right? For J equals to 1, 2, n. Not just that, of course, the vectors V sub 1 through V sub n, they have to be linearly independent because they concatenate into an invertible matrix by assumption. So this is the converse direction of proof. Yes, sir?
That W is, what is that W to
The row of the inverse. So it's just a placeholder for this calculation. Like the W can be W is W sub I is the ith row excuse me, of the inverse matrix for beta. Now, in the case that the basis is orthonormal, if it's orthogonal in length 1, W sub I is literally the transpose of VI. So in the case of an orthonormal basis, it's much easier. We don't actually have to calculate the inverse. We simply transpose the basis matrix that is the inverse. That is the most wonderful circumstance to be in, but we're not always in that circumstance. We're not in that circumstance with the example I had you guys start today. So here's the deal, guys. If we take, all right, I'm going to stick with the basis that we got from my notes. So here's an example. For the A we did at the start of class, which you guys remind me what it was. Help me out here, guys. A was what? Say again? 0, 0? Is, 0, 0, negative 4. 242. 2 what? 0, 6. All right. We found eigenbasis. You guys help me out. What was the eigenbasis that we found over there? What were the eigenvectors in the lambda 2 was what? I remember that the 4 had 0, 1, 0 and minus 1, 0, 1, right? What was the first one? Negative 2, 1, 1. All right. So this gives me the basis matrix minus 2, 1, 1, 0, 1, 0, minus 1, 0, 1. All right? Which tells me that the inverse matrix is what? Answer, I need to phone a friend, all right? Because we're going to get this done in the next 3 minutes. So to calculate the inverse of that matrix, I need technology, right? Because this is not a orthonormal basis. The dot product of these eigenvectors is not, they're not perpendicular, they're not even length 1, right? So we really do need to, we need to use, how do we calculate the inverse of that matrix, right? How do we do that? I think odds of ChatGPT being able to do the inverse matrix calculation are higher than the, the inverse. But I personally like the matrix, this one here. If you look down here, we could either, we could just use a reduced echelon form thing. We've got what? We need to do a 3 by 6. We're going to do the usual thing we do, which is we do what? We put the matrix first, which was what? 0, 0, 0, minus 4, right? And then over here we put the identity 1, 0, 0. It's been a minute since we did this, but you remember. 2. Oh, the basis, yes, thank you. Which, thank you. So I was supposed to put a minus 2 here. 1. Thank you for that very timely comment. 0, 1, 0. I only wish it went tab by tab. I wish you had a feature to go like tab by tab with columns instead of rows, you know? Do I have it right now? I think I have it. So this is the usual, here's how we calculate the inverse, right? All right, so after some calculation, we, uh-oh.
The last column just has a 1 in the bottom part. The last.
Oh. Thank you. That matters. I was like, wow, that inverse worked out really nice. I guess it still works out pretty nice. So doing a matrix, the usual matrix calculation, we get minus 1, 0, minus 1, 1, 1, 1, and 1, 0, 2, right? So that. Going back to your other question, there's your W1, W2, W3 for this particular problem, right? And if we actually work out this matrix multiplication, beta inverse times A times beta, all right? That's going to be minus 1, 0, minus 1, 1, 1, 1, 1, 0, 2. A times beta is going to give me 2 times minus 2, 1, 1, 4 times the vector 0, 1, 0, and 4 times the vector minus 1, 0, 1. So that actually gives me minus 1, 0, minus 1, 1, 1, 1, 1, 0, 2, times the matrix minus 4, 2, 2, 0, 4, 0, minus 4, 0, 4, which if we multiply this, we will get 4 plus minus 2, also known as 2, we get 0, we get 0, 0, 4, 0, 0, 0, 4, which is to say that we've diagonalized it by similarity transformation by the inverse basis matrix. This is how we diagonalize. Find an eigenbasis and then make the basis matrix inverse times A. That brings us to a diagonal matrix. Now, what does this matter? So check this out. If I was going to calculate a to the power n, that would be a real pain. But if I look at it, A is also equal to basis times the diagonal matrix times the basis matrix inverse, right? And if you work that out, you can easily prove that that's beta times the diagonal matrix to the nth power times the beta inverse matrix. I'm skipping a few steps here today, but like an application of this for one thing is if you wanted to calculate the nth power of a matrix, it's super easy if you know the diagonalization, because how do you calculate the nth power of a diagonal matrix? What's d to the n? Well, d to the n is 2 to the n, 4 to the n, 4 to the n, because when you exponent power up a diagonal matrix, you just power up the diagonals. But anyway, so my apologies. Have a good break, guys. I will tell you more after break. So thanks, guys.